This conference will now be recorded.
Hello everyone. The topics that we are going to discuss: anomalous properties of second period elements, diagonal relationship, which is a kind of anomalous property, but this property is important, so we will focus on that. Then periodic trend and chemical reactivity, acidic and basic nature of the oxides of main group elements. So that's all the topics, and there will be also problems related to these topics. Anomalous properties of second period elements. So only second period elements, they will be showing this type of anomalous properties. So here second period is this part. So it is starting from lithium, beryllium. So this is for S block and this is for P block. Okay, only the main group elements. Lithium, beryllium, and then boron, carbon up to neon. So we will focus only on this. Now main group elements, if we look at the first element for each group, for example, when I am talking about lithium, it is the first element of group 1. This is group 1. Beryllium, it is the first element of group 2. Then boron, the first element of group 13, and in this way up to 80. Okay. So elements of the same group, they show similar physical and chemical properties that we already know. So just you take any group, there will be some similarity in physical properties as well as chemical properties. But the first member, there is a little difference. Okay. So the first element for each group. So when it is group 1, the first element is lithium. When it is group 2, first element is beryllium. Then if you move to P block, group number 13 up to 17, the first elements are starting from boron up to fluorine. So all these first members, they will differ from their other family members. Okay. So in certain properties, not in all the properties, in certain properties. Now what is so speciality about these second period elements and why they are behaving in a different way? The reason behind it that we have to know. Here we have a small example. Just take lithium and beryllium. We know that group 1 and group 2, they are very electropositive metals. That is the nature. So they should form ionic compounds, and that is the predominant compound they mostly form. But lithium and beryllium, these two are the first member, they form more covalent type of compound. So this is important difference if we compare with the properties of their other group members. Okay. So this is one of the example. Now what are the different types of anomalous properties? Here the properties are mentioned. The important anomalous properties, one of the most important is diagonal relationship. Okay, we will come to that point later. Before that, you will see that maximum covalence of 4. So when they form compounds, that is by reacting with other elements, you will see that surrounding these second period elements, there are total 4 bonds. That means covalency cannot be more than 4. Another anomalous property, they can form p pi multiple type of bonds. That means 2 bonds, double bond or triple bond that can be formed between 2 second member elements. Okay. So but this type of multiple bond, I mean to say double bond or triple bond, that you will not find for the other members, that is third period or fourth period. This is only for the second period. So these 3 are the anomalous properties of, that is you can see only for second period elements, not for the other period elements. What are the reasons behind it? Small atomic size. So as they are from second period, so obviously their size is very small. This is the first reason. They are second period, so size is very small. Then large charge by radius ratio. Now what it means actually? Large charge by radius ratio, it means compared to radius, the charge is high. So that if we compare with the other group members, just take group 1, lithium, sodium, potassium. Now charge is fixed, that is +1 charge. We know that is the common oxidation state for group 1. So for lithium also it is +1, for sodium also it is +1. So numerator and denominator, if you consider, numerator charge, that is fixed, but the denominator, that is radius, gradually it is increasing as you are moving down. So when you are moving from lithium to sodium, size is increasing. You are moving from sodium to potassium, size is increasing. You are moving to rubidium, size is increasing. That means the denominator is gradually increasing. So numerator fixed, denominator increasing. That means the ratio as you are moving down, it will be smaller and smaller. So for the first member, that is lithium, it should have the maximum ratio, that is large ratio. So this is the second reason. The third reason, high electronegativity. We know down the group as we move, electronegativity decreases. Metallic property increases, electronegativity decreases. But when you consider the first element, that is the second period, obviously high electronegativity. And the fourth reason is very crucial. Why? Because you will not find d orbital, because in second period there is no d orbital. But when you move to third period, that is sodium, magnesium, aluminium, for all these elements there is presence of 3d. Though it is true 3d is vacant, there is no electron in 3d, but there is availability of 3d. So as a result, what happens? Suppose when there is electron in 3p, suppose this is 3p and there are some electrons. So just take oxygen, there will be sorry, not oxygen, sulfur 3p, this one which is group 16, so total 6 valence electron. So there will be 2 electron in 3s and 4 more electron in 3p. Now in 3p you can see there are total 4 electrons, right? But when it is vacant 3d also present, I am just drawing it partially. Now what can happen? This electron which is in paired condition, you can unpair it and this electron can be shifted here. Similarly, the pair of electron that you are seeing in 3s, that can also be shifted here. So as a result, now you can get total how many unpaired electron? You can get total 6 unpaired electron. And all these unpaired electron can take part in bonding. But when it is second period, this type of d orbital is not available. So if there is any paired electron, suppose for oxygen there is paired electron, or if you consider nitrogen, there is 2 electron in 2s. So you cannot make it unpair and you can shift it to d. That is not possible. That means they cannot expand their valency up to a certain point. But if you move to third period or other period, now because of availability of d orbital, 3d, 4d, 5d, now number of unpaired electron can be increased. So that is the reason absence of d orbital in the valence shell of second period elements. This is one of the important reasons for which they are showing anomalous properties. Okay, so we will see example that in this question that boron forms Bf4 minus. Bf3 is neutral molecule, but if with Bf3 you add F minus, now it will become Bf4 minus. Similarly, AlF6 3 minus. Now boron and aluminium both are from group 30. See, but boron is from second period, aluminium is from third period. That is the difference. So see, both are forming some anionic type of compound with fluoride ion, but their formulas are different. In case of aluminium, total 6 aluminium F bonds are present, but in case of boron, it is maximum 4. So why the formula is different? They are from same group, so they should behave similarly. There should be similar type of structure, but no, it is behaving differently. So this is the actual structure. BF total maximum 4 bonds you can get because it is second period. So maximum covalency 4, you cannot get more than that. So in aluminium, because of presence of vacant 3d, it can expand its covalency because the number of unpaired electron can be increased. But in case of boron, that you cannot do. Okay, and not just always that there will be unpaired electron, that is by shifting electron from 3s or by shifting electron from 3p to 3d. That may happen sometime, but another thing can also happen. In this case, the F minus that is present, they can also donate electron to 3d, and in this way it can form bond. Okay, but in case of second period, there is no vacant d orbital. So any ligand or anion, if it wants to donate electron, the rooms are not available like this. Okay, so that is why the formulas are different. So this is one of the anomalous property. Next, as it is mentioned in the previous slide, they can form pi multiple bond. So if you look at these bonds that are written here, CC double bond, triple bond, that means carbon nitrogen, they are from second period, right? So they can form this type of bonds between similar type of atom, but they can also form with other second period elements. So carbon can form double bond, triple bond with the similar atom, that is same carbon, but it may be any other element. But see, whatever atoms are mentioned here, all are basically from second period. Okay, so they can form multiple bond between same element or to any other second period element. So two properties you are seeing in this slide, one is maximum covalency 4 and they can form pi bond, and the most important anomalous property is diagonal relationship. So now we will see that. Just look at this picture. Here we have taken group 1, 2, 13 and 14, partial picture of the periodic table. Now when it is lithium, which is the first member of group 1, you can find some similarity, that is similarity in properties, with the next group element and also the next period element. So magnesium is the element which is next group and also next period, because magnesium is third period and group second group. Okay, so there will be some similarity between these two, and their position in the periodic table is diagonal. It is not that magnesium is just below lithium or it is just right hand side of lithium. No, it is present in the diagonal position. So that is why diagonal relationship. Similarly, if you take beryllium and after that if you consider the group P block, omitting the D block, you will find some similarity between beryllium and aluminium. Then boron is having some similarity with silicon. In this way it will go on. Okay, so in these anomalous properties, that is diagonal relationship, they resemble the second element of the following group. Following group means next group, and second element means the next period element. So that is diagonal relationship. Now when two elements will behave similarly, what are the necessary conditions? Just forget about diagonal relationship. Simply suppose I am asking you when elements will show similar type of property. Now the answer is when they are having similar type of size, whether it is ionic size or atomic size, their electronegativity should not differ much. It should be close value. And polarizing power. Now what is polarizing power? Polarizing power is basically this ratio. So this ratio you have already seen in the previous slide, charge and size. So polarizing power, that is directly related to charge by size. Higher is the ratio of this charge by size, higher will be the polarizing power. Fine. And we know that polarizing power is very charge by size. This is large. Remember in the first slide it is mentioned in this reason box in the right hand side that large charge by radius ratio. That means polarizing power will be high for the second period elements. Now if you look at this table, you can find some trend. So when it is electronegativity, across the period it increases, down the group decreases. When you consider size, we know across the period decreases, but down the group increases. Charge across the period increases. So what it means by charge? So suppose you have lithium, it can form maximum +1. Then beryllium, it can form +2. When it is boron, it can form maximum +3. So in this way, charge will increase as you are moving from left to right. And what about charge and size? See, when you are moving across the period, the numerator, that is charge, is increasing, size is decreasing. That means this is decreasing, this is increasing. So obviously across the period it will increase, right? And charge, when it is down the group, it remains same, because down the group it is a similar type of behavior. So more or less it will remain same. There may be some exception, but in general it remains same. So and charge by size, it decreases down the group. Okay, because charge by size, okay, size increases down the group and charge remains same. That means obviously The numerator is fixed, denominator is increasing, so charge by size that will decrease. So these are the orders for these 4 properties. And it is already mentioned that elements will show similar type of property when their sizes are similar, electronegativity is similar, and this ratio is similar. So that is why we are having all these properties, how they are changing across the period and down the group. Now you can see mostly it is these factors are working in opposite direction. So electronegativity across the period increase, then down the group decrease. Size decrease, then increase. So it is working in opposite direction. So these factors are working in opposite direction. So that is the reason now when you are moving in this direction, it is a type of change. When you are moving downward, it is another type of change. That means now when you are moving in diagonal direction, these two effects are compensating each other. So as a result, what will happen? When you are moving from lithium to Mg or Be to Al, because of this compensation, they are working in opposite direction. Now they will balance each other, and ultimately the properties, that is this electronegativity, size, then charge, then polarizing power, all these properties, there will be similarity for these diagonal members, that is lithium Mg, beryllium aluminium, boron silicon. Okay, so these are the reasons behind their diagonal relationship. That is why they are behaving different similarly. Here we have question related to this discussion. Among the statement 1 to 4, we have total 4 statements. The correct ones are: the first statement, beryllium has smaller atomic radius compared to Mg. Now all these statements, how many elements are there? We have Be, which is from group 2. After Be, the next element is Mg. And if you consider group 13, there is aluminium. Sorry, it is a position is not correct. The position is like this. So after beryllium, there is actually boron, but it is not present. I am not writing it. After Mg, there is A. So these are the position of these 3 elements. Now beryllium is having smaller atomic radius compared to Mg. This statement is correct or not? Obviously, this is correct because as you are moving down, Mg will be having higher size. So this statement is true. Now it is very easy to understand, right? Now 1 is present in option 1 and option 3 and 4. So you can cancel this one based on this. Now Be has higher ionization enthalpy than aluminium. Now Be, when you are moving to, sorry, yes. So when we are moving from beryllium to the next element, it is boron. What we know that ionization energy when you are moving from left to right, it increases because size decreases. And when we are moving down, then size increases. So that is why we can easily remove the outermost electron. Fine. So for aluminium, what will happen? That is beryllium has higher ionization enthalpy than aluminium. Okay. Now, as they are, just look at this previous beryllium and aluminium, there is some diagonal relationship. So at a first glance, what it seems that it should be exactly same. But what happens? Though there is some diagonal relationship, it is not necessary that everything will be exactly same. Okay. So if we just for the moment, if we keep this statement aside and jump to the next one, so that if in any statement, if you are having any doubt, just keep it aside and go to the next statement. So the next statement here we have charge by radius ratio for beryllium, it is greater than that of aluminium. Now charge by radius ratio, as we have seen in the previous table, because of similarity in properties, that is charge by size, electronegativity, because of similarity there is actually diagonal relationship. So if that is true, that means this charge by radius ratio, that should be similar type for Be and aluminium. Okay, it should not be that Be is greater. So it will be, should not be correct. And the last one, both Be and Al, they form mainly covalent compounds. Now beryllium, the first paper, it forms covalent compounds, and aluminium, because of this diagonal relationship, that is also basically correct. So if 3 is correct, 4 is also correct. That means 3 and 4, that is present together in which option? It is present in option 4. Okay. So beryllium has a smaller atomic radius compared to Mg, that is correct. So it is fine. And Be has higher ionization enthalpy than aluminium. Now, according to diagonal relationship, it seems it should be same. But what happens because of the electronic configuration of beryllium? See, it is like this: 1s2, 2s2. But if you consider aluminium, the electronic configuration is 2s2. Obviously, 1s2. I'm just writing the outermost. Sorry, 3s2, 3p1. That is the configuration for aluminium. Now this removal of this electron, it is very easy process, because when you are removing this, it is reaching the stable fulfilled configuration of 3s2. So it is less facile process. But when you consider Be, it's having configuration which is also already fulfilled. Now to break this fully filled orbital 2s, it requires energy. So that is why it is higher ionization enthalpy. So don't think that Be and A, they are diagonally related, so everything will be exactly same. No, it is not like that. There is some discrepancy also because of this special type of electronic configuration of beryllium, right? So this statement is basically correct. So this is also true. Okay. Now 3 is not correct because this ratio, it is actually similar type of ratio. So 3 is not correct, and 4 that is correct. Now if we omit 3, it is already cancelled. This is also cancelled, right? So 1, 2, 4. Sorry, I just mentioned that 4 is correct, but that is by mistake I have said, because charge by radius ratio, this is actually same for both these elements, Be and Lb. So that is why 3 cannot be correct, it is false, and this is true. So 1, 2 and 4, these 3 are correct. So 1, 2, 4 correct means option 1 should be the correct option. So after these anomalous properties, next topic is periodic trend and chemical reactivity. Physical and chemical properties of elements depend on the valential electronic configuration. So that is said several times, we already know that. Now when there is compound formation going on, that is a bond is formed, a new bond is formed, a old bond is broken, then what happens? This new bond, it can be formed in different way. It may be sharing of electrons. That is, suppose there is a bond between A and B. So one electron given by A, another electron given by B, and now they are sharing this. Or sometimes it may be that one element is completely losing electron, another element is completely gaining electron. In that case, one will be forming cation, another one will be forming anion, and there will be some electrostatic interaction between this anion and cation, and this is ionic bond. So new bond can be formed in different way. It may be that electrons are shared, or it may be complete loss of electron from one element, complete gain of electron from other element. Different ways compound may be formed. Now higher the reactivity of the element, obviously the easier it is to combine. That is, easily it will take part in reaction. That is, you can say the element is reactive element. Hence the electronegativity and ionization energy, these two properties determine a chemical reaction. Now, how it determines? Suppose I am saying ionization energy is very, very high. That means you cannot remove the outermost electron very easily. So it cannot generate cation very easily. Similarly, if it is having very low electronegativity, it will not attract electron. Okay, so these two properties you can say as if it is opposite. That is, ionization energy, from this property you can understand how readily it can lose an electron, and from electronegativity you can understand how readily it can attract electron. So these properties are important. So if you know the trend of these properties, that is, if you know how ionization energy is changing, across the period or down the group, if you know how electronegativity is changing, obviously you can have some idea about the reactivity of the elements. Fine. Elements of the periodic table, if you focus on the left hand side, we know they are mostly metallic, that is the S block I'm talking about, and ionization energy is very low. That is, in the whole periodic table, if I say that which part is all the elements are having low IE, and that is actually the left portion, and that is the reason they can readily lose their valence electron, and that is actually metallic character. Fine. Now if you go to the right hand side of the periodic table, you will see mostly there is high electronegative elements, especially if you move to top right corner, most highly electronegative, or you can say high electron affinity. That means their electron gaining enthalpy is very high. They try to gain electron very easily. Mostly the top right corner, though in general I'm saying right side, but mostly the top right corner. So both this part, left side metallic properties predominating, right hand side non-metallic properties predominating, that means high EA or electron affinity or high electronegativity, like this. So they can easily accept electron. So from these two statements, what conclusion you can draw? That when they will form compounds between them, as if they can easy, that is, as if these two extreme, left extreme, right extreme, these two extreme are very reactive extreme, right? So S block elements, they can easily form compound with the non-metallic elements that are present in the right hand side. Now as a result, elements of these two extremes, they show high reactivity, obviously compared to the other members, sorry, not members, other elements that are present in the middle part of the periodic table. Now what about noble gases? Because their configuration is fully filled, completely filled, NH2 and P6. So there is no tendency to accept electron or lose electron. So when you will see any compound of noble gas, that means you have to, when making these compounds, high energy is required. Otherwise it is not possible. And only one or two element in the noble gases, if you consider, you will find some compounds. Mostly xenon, this noble gas, its compounds are very common, but not other members. But that is very rare case and highly energy requiring process. So mostly in general, they do not take part in reaction. So that is the reason we call them inert gas. So based on this chemical reactivity, whatever we have discussed, let's solve this. There are 4 statements. So following statements are regarding the periodic trend of chemical reactivity of alkali metals, that means group 1, and halogens, that means group 70. Two extreme, right? So if I draw a periodic table like this is group 1 position, and extreme right is basically noble gas. So group 17, it is somewhere here. Okay, this is 1, this is 70. Now following statement regarding the periodic trend of chemical reactivity of alkali metal and halogens are given. Which of these statement gives the correct picture? The first statement is saying the reactivity decreases in the alkali metals but increases in the halogens with increase in atomic number. Now with increase in atomic number, it basically means when you are moving down, because only when you are moving down in a particular group, atomic number increases. So when you are moving from lithium to sodium to potassium in a particular group, I mean in this case it is alkali group, atomic number increases. So basically it is another way of saying when you are moving down the group, reactivity decreases in case of alkali metals but increases in case of halogens. So is this correct? Now down the group, reactivity doesn't decrease for alkali metals, it basically increases. Metallic property is more and more, and ionization enthalpy is becoming less and less, so it can easily lose electron. That is, compared to lithium, so potassium can easily lose electron, so it will be more reactive. So decreases, this is not correct. But what about the second part of the statement, that increases in halogens with increase in atomic number? Now when you are moving down, that is, you are moving from F to Cl to Br to I. So these are all the halogens. Now down the group, electronegativity decreases and non-metallic character also decreases. So mostly the upper elements, that is FCl, these two will be more reactive compared to Br and I. So down the group, reactivity basically decreases. So this is also not correct. Now come to the second statement. Basically this decrease and increase different types of permutation combinations. So in both it is saying decrease, it is increase. Then the second statement, in both alkali metals and halogens chemical decrease. So it is both decrease with increase in atomic number, but that is also not correct. Come to the third one. It is saying that chemical increases with the atomic number down the group in both. So now it is both increase. Now this is also not true. Only the last one is true, because reactivity is basically increasing down the group, and for halogens it is basically decreasing. So the most reactive part in the left hand side, if we consider, it is basically down left part, and for halogens it is the upper left, upper right part. So this is the most metallic part in the whole periodic table. This is the most non-metallic part in the whole periodic. So they are very reactive and they can form compound with each other, and mostly it will be ionic type of compound, because metals are ready to lose electron, non-metals are ready to accept electron. So positive charge and negative charge, fine. But correct statement here is the last statement. Okay. Let us analyze this acidic and basic nature of oxides. So now we have some idea, that is mostly in the whole periodic table where the metals reside. In the last problem I have just said they reside mainly in the left hand side, but in left hand side which part, it is mostly the downward. As you move down, the metallic nature is very high, but in general you can say that all the metals are towards the left hand side. Okay. And non-metallic nature, it is maximum in the right hand side and mostly in the upper right hand side, and in between you can expect some that is not very metallic or not very non-metallic, something in between. But what about this acidic and basic nature of oxide, how it is related to metallic and non-metallic nature? Yes, it is directly related. So that is why I'm talking about this metallic nature and non-metallic nature. Fine. So when it is metallic nature, you will see the corresponding oxide is mostly basic, and when it is non-metals, the corresponding oxides are acidic in nature. Okay. So let us analyze the nature of compounds formed by taking two elements from two extremes. So we have taken one element from alkali metal, which is sodium, another element from halogen, we have taken chlorine. Now both are reacting with oxygen, but what type of compound we are getting? We are getting here sodium oxide, and this is chlorine oxide. Now, though it is also true that it is not the only oxide of chlorine, basically chlorine can form any other types of oxides also, but we have taken this one, Cl2O7. Now among these two oxides, as sodium is metallic in nature, so Na2O will be basic oxide, and chlorine is non-metallic in nature, it will be acidic oxide. Now as it is basic oxide, when you are adding water to it, the compound that you get, it will produce a strong base. You know, sodium hydroxide, it is a strong base. Similarly, if you take Cl2O7, as it is acidic, so when water is added, you will get this type of acid, which is known as perchloric acid. Though I am saying that there are other types of chlorine oxides also, and if you add water, you will get some different types of acid. But in this case, we have chosen Cl2O7, and when it reacts with water, you get HClO4, which is perchloric acid. So here in the previous case it is producing base, in this case it is producing acid. So this the proof that sodium is metallic oxide and chlorine oxide is acidic oxide. Now what about the elements that are in the center? So in the center you can find some elements, that is aluminium, then carbon, nitrogen. Carbon, nitrogen, they are from, remember, which group? Carbon is group 14, nitrogen group 15, aluminium is 13. So they are in the middle part, not extreme right or left. So they are compounds, they are oxides, they are amphoteric and neutral. Now what it means, amphoteric? Amphoteric means it can show basic property as well as acidic property. Both types of property they can show. And what about neutral? Neutral means there is, it will not show acidic property, it will not show basic property. So these amphoteric and neutral, they are not extreme like basic nature or acidic nature. They are something in between. Either they will not react at all, that is they will not show any property, basicity, acidity like neutral, or they will show both the property. That is actually amphoteric. So as we move, some examples if you see, as we move down the group, we know IE decreases and metallic nature increases, or you can say electropositive character increases. IE decreases, electropositive character increases. Now if you take group 2 elements, so here you can see group 2 elements. First element is Be, then Mg, Ca, strontium, barium. So in this way, as you are moving down, you are getting these elements. Now the first element Be is its hydroxide, not just oxide, we will also discuss about hydroxide. So here I can write hydroxide also. Basically with non-metals we do not get hydroxide, so that is why in the topic only oxides are written. So BeOH whole 2, MgOH whole 2, that is for the first two elements, the nature of their hydroxide is amphoteric. Come to the next one, Ca is not mentioned there. Okay, go to Ba. It is actually, sorry, one thing I missed, not both of them. Be, the first member, it is amphoteric. Then as you move to Mg, there is weakly basic nature, not strong. But then if you go to the extreme B, last element, it is very strong, strongly basic. Similarly, if you go to group 15, in group 15, the first one is nitrogen, phosphorus, arsenic, antimony, bismuth. So the first element, it's oxide, NO2, and the second element, phosphorus, it's oxide. These two, they are mostly non-metallic, and that is why their oxides are acidic. Now one thing if strikes you, that here it is mentioned nitrogen is showing neutral oxide, but here it is showing that NO2 is forming acidic oxide. That means why this, actually don't think it as discrepancy, it is because though it is same element, that is nitrogen, the element is fixed and there are different types of oxide, NO, N2O, NO2, and there is other oxides also, N2O5. But what happens in case of NO and NO2, here oxidation state of nitrogen, it is towards lower side. So it is not just, it is true that once you know it is metallic element or non-metallic element, you can have some idea that whether it will be basic oxide or acidic oxide. But another point is also there, and that is oxidation state. Suppose when the element is fixed, that is same element, but now you have different types of oxide. You have NO, you have N2O, you have NO2. Now oxidation state is different. So in NO, oxidation state of nitrogen +2. Then in case of N2O, because oxygen is -2, so it will be +2. In case of N2O, it is N2O. That means here also oxidation state is low. But in case of NO2, 2 oxygen, that means total negative charge -4. So total positive oxidation state will be +4. So oxidation state when increases, what happens? Element is fixed. Oxidation state is changing. Then also you will see higher is the oxidation state, more it will be towards acidic side. Okay. So P2O3 NO2, these two are the first elements oxide, so it is acidic. Then arsenic, antimony, they are amphoteric. And the last one, because of its metallic nature, oxide will be basic in nature. Fine. So the picture that you are seeing here, so this two part is S block and this part is P block. Okay, so in S block, this blue color, it is basically showing basic character, and down the group there is increase in basic character, that is also mentioned. Now this green color, it is basically in between, that is either amphoteric or it may be neutral. And what about the red color? Red color, it is the indication of acidic nature of the oxide. Fine. Now in some cases you can see some merging of two different colors. So why it is so? Here you see it is mentioned AS2O5 and AS2O3. So same element, but oxidation state is different. So when it is AS2O5, then it is showing red color. That means it is acidic. But when it is AS2O3, now it is towards green side. That means it is not acidic, right? It is either neutral or amphoteric. So in AS2O5, the oxidation state of arsenic is basically +5. But in arsenic, it is +3. So higher oxidation state means it will be towards acidic region. Similar is also for Sb2O5, Sb2O3. So in a given period of the periodic table, the oxide progress from basic to amphoteric and finally acidic. So if you focus on a particular period, suppose I am taking here third period. As you are moving left to right, first blue, then green, then red. That means basic, amphoteric, acidic. For example, third period elements, here it is mentioned, SiO2, Al2O3 is amphoteric, SiO2, though it is in red region, but it is weakly acidic. Then P2O5, P2O3, all these different sulfur, sulfur, phosphorus, chlorine, all oxides are acidic in nature. Acidity, as I have already mentioned it, now see this point, acidity also increases with an increase in the oxidation number of the same elemental oxide. So this I have already mentioned. This one, because of its high oxidation state, +5, it is more acidic. This is not so acidic. Okay. Similar is also for these two, and you can see some magnesium compounds here. Though it is a D block, but still you can take it as example. So as we are moving from Mn2O7 to Mn2O3, oxidation state here it is +7. Then in this case it is +3. Here it is +2. So as oxidation state is decreasing from Mn2O7 to Mn2O3, acidic nature is also decreasing. Okay, but these two you can already see in this picture. Right? Which one of the following orders presents the correct sequence of the increasing basic nature of the given oxide? So you have to find correct sequence of increasing basic nature. How many elements are there total? There is potassium, sodium. So potassium and sodium, they are from group 1. Then we have Mg, which is from group 2. So the position of Mg is just after Na, and we also have aluminium. Now aluminium is omit the D block. Next group is 13. So aluminium is here. So these are the, so whenever you are getting this type of compound, it is better if you just write their position or just imagine their position in the periodic table. Fine. Now we have to find correct sequence of increasing basic nature. So before going exactly to the question, you have to basically find the correct sequence of metallic nature, because metallic nature, that is directly related to basic nature. So what you should do, you should first find which element is maximum basic. Now down the group, metallic nature increases. Sorry, I am trying to say which element is maximum metallic, just focus on that. So when you are moving down, because these three elements are group period 3. This is third period. This is fourth period. So only potassium is from this period. Now here the metallic character obviously it will be maximum. Sodium is more metallic compared to Mg and Al. That is fine. Now, in between Na and K is more metallic, even more metallic than sodium. So the order is K, Na. Now, probably you can understand why I am saying Na is more metallic than Mg, Mg is more metallic than Al, because as you are moving from left to right, metallic nature is decreasing and non-metallic character is increasing. So that is why sodium is more greater than Mg. Then after Mg, it is aluminum. So this is the metallic property. Now once you know this, you can easily understand what should be the basic nature correct sequence. So the oxide of potassium, K2O, that should be most basic. After that, Na2O. The formulas are obviously different because oxidation, depending on oxidation state, formula will be different. Okay, so potassium and sodium, similar type of formula because their oxidation state is +1. For both it is +1. For Mg it is +2, and for aluminium it is +3. So oxidation state is different. That you don't have to focus. I'm just writing it so that you can understand why the formulas are different. So from this discussion, it seems that first option, that should be the correct option, right? Next question. Which of the following dioxide is amphoteric in nature? So it is not asking acidic, it is not asking basic, it is asking which one is amphoteric. That means it should show both the properties, right? Now, you just have a look in this. So how many oxides we have here? CaO, SiO2, carbon dioxide, SnO2. CaO, SiO2, carbon dioxide, SnO2. Fine. Now there is another oxide of Sn also, that is basically SnO. That is not mentioned here, but there is another oxide also. So these four are basically mentioned in the question, right? But if you just can't remember that table, what you can do, you can write the position of these elements: calcium, silicon, carbon, tin. So calcium, it is from group 2. Potassium and then calcium. So it is 4th period, and we have group 14. There is carbon, there is silicon, and we have tin also from group 14. So these are there, that is more or less, not that is exactly, I have not written it. So these are the positions. Fine. Now obviously this will be towards left hand side, and it is from S block, so it will show basic nature, right? And the chance of amphoteric nature, it will be mostly either carbon, silicon, or tin. Now carbon, silicon, tin, all are from same group, and we know as we move down, metallic nature increases. So carbon, its oxide, it should show acidic nature. So CO2 is basically acidic nature. Though there is another oxide of CO, remember, which is carbon monoxide, and carbon monoxide basically it shows neutral oxide, but that is not mentioned here. Here CO2 is mentioned, so you just have to focus on CO2. And among CO and CO2s, in CO oxidation state of carbon is less, in CO2 it is high, so it is showing acidic character. So CO2 cannot be amphoteric. Then among SiO2 and SnO2, this is a single choice answer. So obviously among SiO2 and SnO2, the chance that SnO2 will be more amphoteric in nature compared to SiO2, right? Now as if you consider the definition of, that is amphoteric nature, it can react with both acid as well as base. So SnO2, see the first reaction, it is reacting with HCl and it is forming chloride of tin and water. In the second case, it is reacting with base, which is sodium hydroxide, and it is forming sodium stannate, Na2, that is total positive charge 2 plus, SnO3 2 minus, sodium stannate. So this reaction, that is the proof that here amphoteric character is shown by SnO2 but not the other elements. CaO is metal, it is basic oxide, SiO2 CO2 acidic oxide. Only SnO2, it is also in group 14, but it is towards, as you move down, is mostly it will show metallic nature, so it is amphoteric. Three elements X, Y and Z, they are in third period of the periodic table. So these three elements, what are the elements? That is not given. What is given? All of them are from third period. Now the oxides of these three elements respectively, it is already mentioned that basic, amphoteric, acidic. That means X is basic because respectively is written. X is basic, amphoteric is Y, Z is acidic. You have to find from this information the correct order of atomic number of these three elements. Now what elements they are, that you don't have to know. From this information that X is basic, Y is amphoteric, basic, amphoteric, acidic. This information is enough to understand their correct order of atomic radii because they are from same period. So you can write them in the same line, in the same row, and as you move from left hand side to right hand side, we know what happens. It becomes basic, then amphoteric, and then acidic. Now left to right, when you are moving in the same period, obviously atomic number increases. So it means that Z should be higher atomic number than Y. Y should have higher atomic number than X. So which option is correct? Option 2 is correct, right? The correct statement among 1, 2 and 3 regarding group 13 element oxides, that we have to find. So here total 3 statements are given, 1, 2 and 3. And in option 1, 2, 3, 4, different combinations of these 3 statements are there. Now all these statements are regarding group 13 elements. Group 13 element means boron, aluminium, gallium, all these are group 13. Indium, then thallium, Tl. Okay. So as you are moving down, you are getting all these elements. The first statement, boron trioxide is acidic. Then oxides of aluminium and gallium, they are amphoteric. That means these two amphoteric, this is acidic, and oxide of indium and thallium, they are basic. This is the next one. So it is actually saying the correct thing because we know when we are moving down, metallic nature increases. So obviously when metallic nature increases, the basic nature also increases. So first acidic for boron, then aluminium, gallium, these two are amphoteric and these two are basic. So it is exactly fine. That means all these statements are correct. Now in which option all these statements are present? 1, 2 and 3, it is option 2. Okay. Number of amphoteric compounds among the following is, here we have beryllium oxide, which is from group 2, that is Be is from group 2, right? Then we have Ba, that is also from group 2. Then we have again beryllium, but now it is hydroxide, and we have strontium hydroxide. So Be, after that there is Mg, but I am not writing that directly, I am writing Sr Ba. So these are their positions, but they are from same group. So we have to find amphoteric compounds. Now mostly amphoteric compounds are formed by Be. And here we have two Be compounds. One is oxide, another one is hydroxide. So BeO, then BaO, it is amphoteric. This is also amphoteric. But Ba and Sr, that means strontium and barium, as they are in the down, that is when you move downward you get them. So first Be, Mg, calcium, barium, and in this way you are moving down. That means they are the last two elements. So obviously they will be basic in nature. SROH hold to basic, Ba, Sr, they are basic in nature. They form alkaline solution in water. So here these two are amphoteric. Number of amphoteric compounds among the following. It is actually integer type of question because there is a fill in the gaps. It will be 2. These two. Last question. The total number of acidic oxide from the following. So here how many compounds are given? NO, N2O. So these two are nitrogen. Then we have boron, another nitrogen. Then we have carbon monoxide, SO3, and P4O10. Now remember, total 3 nitrogen oxide. But among these 3 nitrogen oxide, only this one is acidic in nature. The other 2 oxides are not acidic, they are neutral. Okay. Then B2O3, and that is acidic. CO, carbon monoxide, is not acidic. CO2 is acidic, and that depends on oxidation state. Remember, same element, different oxidation state. When present, higher oxidation state will be acidic. Then we have SO3 and P4O10. Now these two are also acidic in nature. So here among these total 7, neutral is total 3. But how many acidic oxides are there? That is 7 total minus 3, 4. So this option should be the correct option. Okay. So this chapter is complete. So though we have some time, but I will not proceed anymore. We are ending the session here. Thank you for this.
This conference will now be recorded.